Hey, what's up everyone? Today we're going to be talking about integrated rate laws. So remember from your rate law, your rate is equal to K times the concentration of A to some power M times B to some power N. And your rate tells you your instantaneous rate of change. So at a given instant, how fast is is your reactants changing? How fast is the concentrations changing? Sometimes you're not going to want that instantaneous rate of change. Sometimes you're going to want the change in your concentration. So you want your final concentration and your initial concentration. And your integrated rate laws helps you do that. Integrated rate laws relates the time and the concentrations of reactants. And you'll see in the integrated rate laws that we do that that the concentration at a given time is always going to be a function of your rate constant and your initial concentration. So your rate laws are different depending on what order you have. So we're going to go through the first three orders today. So 0, 1, and 2. Let's start with 0. For zero order reactions, your concentration at some time t is going to be equal to minus kT plus your initial concentration. You'll notice that all your integrated rate laws are in the form of y equals mx plus b. So you can end up graphing them and you'll see the slope that you get. In this case, the graph of the concentration with respect to time is linear and has a negative slope, the slope being the negative k, that's your m here. And that's your integrated rate law for zero order reactions. Your t1/2 here represents your half time. So how long does it take for the reactants to be at half of its initial concentration? In zero order reactions, since your rate of change is always constant, it means that it's just going to be at half the time. So you can get this you can get this form by just plugging it into the integrated rate law that we have here. So you're gonna want your concentration at some time t to be half of your initial concentration. So if we plug that into our equation here, 0.5 times your initial concentration is equal to minus kT plus your initial concentration. That'll get you that kT is 0.5 times your initial concentration. So your time is your initial concentration over 2K. And that's what you have here. That'll be the process for finding the half times for all of your reactions depending on the order. And we'll see that in first and second order as well. So in first order, it tells you that the natural log of your concentration at some time t is equal to minus kT plus the natural log of your initial concentration. And of course, it's in the form of y equals mx plus b. And the same thing here, the graph of your natural log of your concentration at some time t with respect to time is linear. It has a slope of negative k, and that's the thing about your zero order and your first order, the slope is negative. All right, let's look at your half time. So you know that the concentration at some time t is just going to be 0.5 of your initial concentration. So if you plug that in, the natural log of 0.5 of your initial concentration is equal to minus kT plus your the natural log of your initial concentration. And you can move this around a little. So kT is the natural log of 2. You can subtract the natural logs, and then using log properties, you can cancel out the initial concentrations, and you're just left with 2. So your time is the natural log of 2 over k. This is the time at which the concentration at a given time is half of your initial concentration. And that's first order reactions. Second order reactions are a little different. It's the reciprocal of your concentration at some time t. That's going to be equal to kT plus 1 over your initial concentration. So if you look at the graph, of course, it's in the form of y equals mx plus b. If you graph the reciprocal of your concentration at some time t with respect to time, that is a positive slope. The slope is k, and your half-life is 1 over k times your initial concentration. So I'm not going to show that. The only one that you really need to know for half-time is your first order reaction. Your first order reaction has the half-life of the natural log of 2 over k, and that comes in handy because nuclear decay uses first order kinetics. So the half-life of anything radioactively decaying is the natural log of 2 over your k, your rate constant. All right. Again, remember the zero order and the first order has a negative slope. It's negative k, but the second order has a positive slope. So that's one distinction that you should know. Let's do one example just to solidify everything. For an irreversible reaction A to products, the graph of the reciprocal of your concentration of A as a function of time is linear. What is the reaction order in A? The fact that the graph of your reciprocal over time with respect to time is linear, the fact that that's the case is indicative that you're dealing with a second order reaction. So this is second order. If you actually looked at the graph, it would be like a positive slope. This would be your concentration initial, the reciprocal of it. The slope would be k. And yeah, of course, in the x-axis, you have time. So if you see 1 over the reciprocal with respect to time, that's second order. Natural log with respect to time, that's first order. And the concentration itself with respect to time is zero order. That's how you use the integrated rate laws to find your concentration of a given reactant at a certain time. Of course, given your reaction order. And that's all I have. I hope this was helpful. I'll have a video coming up really soon about the derivation of your integrated rate laws. If you would like to look at that, it involves some calculus. But other than that, that's all I have. I hope this was helpful, and I hope to see you later. Thank you.